Welcome everyone. Let's dive right into our structured explainer on unlocking two-dimensional vectors for your Cambridge exams. I want you to think of today's session as planning the absolute perfect heist. You are the mastermind, your ocean, and your ultimate target is the vault, a flawless score on your mathematics exam. But pulling off the perfect answer heist? Well, that requires you to assemble a team of cognitive specialists and absolutely master your toolkit. You know, we see students lose marks every single year because they treat vector questions like basic everyday arithmetic. For instance, let's talk about two hypothetical students we see all the time. First, we have Alex. Alex overloads his answers with raw mathematical facts, but completely lacks analytical direction. Then we have Sam. Sam rushes through his working, panics under the timer, and completely misses the specific command word requirements from the examiner. We are going to fix those exact errors right here, right now. We are going to build your master toolkit so you can walk into that exam room completely bulletproof.
We are going to systematically build your vector toolkit today through 5 very logical steps. We're going to cover vectors versus scalars, speaking the vector language, core vector operations, zero and unit vectors, and finally, we'll tackle those tricky real-world velocity applications. Let's get right to it.
Section 1. Vectors versus scalars. We need to master the art of measuring movement.
To start, we need to completely isolate the core difference between the two main ways we measure movement in physics and mathematics. Imagine a real Cambridge mathematics past paper question asking for a velocity calculation. You've got the clock ticking down. Alex just writes down a number, Sam writes down a number and a completely wrong unit, and guess what? Both get glaring red pen marks from the examiner. Why does that happen? Because they fundamentally miss what the command word velocity actually demands. Here is the golden rule. A vector is a quantity that has both magnitude, which is just a fancy word for length or size, and a highly specific direction. If you are planning our getaway heist and I tell you to drive the getaway car at 100 kilometers per hour, that information is totally useless if I don't tell you to drive 100 kilometers per hour north towards the safe house. When the examiner asks you to calculate a vector, your structural Peel framework must kick in instantly. Point, evidence, explanation, link. You have to combine both that magnitude and that specific direction to get the marks.
And this brilliantly illustrates the contrast. A scalar, like speed, just gives you a number. It's a raw fact. But a vector, like velocity, demands both the number and the compass direction. Let's look at Alex's flawed answer again. The question explicitly asked for velocity. Alex gave a speed of 60 kilometers per hour. That is a scalar. It only has magnitude. The examiner strikes it out immediately. 0 marks. To get that beautiful green check mark, Alex needed to state the vector, a velocity of 60 kilometers per hour south. In your exams, every single time you see a quantity, your brain should automatically scan and categorize it. Is this a scalar or a vector? Think about it. Weight? That's a vector because gravity physically pulls it down in a direction. Mass? That's a scalar. It's just an amount of stuff. Speed? Scalar. Velocity? Vector. This is the foundational rule that guarantees those top marks.
Section 2. Speaking the vector language. It's time to decode the exam.
You can't hack the vault if you can't read the code, right? Whether you see a vector written with bold I and J components or stacked vertically in a column, it is simply telling you the exact horizontal and vertical distances to travel. In component form, 4i plus 3j is perfectly identical in meaning to the column vector with a 4 on top and a 3 on the bottom. The I is always your horizontal movement across the x-axis. A positive 4 means 4 units to the right. The j is your vertical movement up the y-axis. A positive 3 means 3 units straight up. Now, when Sam is rushing, if he sees a coordinate, say 4, 3, and a column vector, 4 over 3, he often confuses them. Don't do this. A coordinate is a static location on a map. A vector is the journey itself. It is the literal step-by-step instructions on how to get from point A to point B. Before we continue, subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
If you need to find the modulus or magnitude of a vector, you simply use your trusty Pythagorean theorem. Why? Because the x and y components always form a perfect right-angled triangle. This is where your strategy truly elevates above the average student. The command word here on the exam paper is usually find the magnitude or calculate the modulus, and it's sometimes denoted by 2 vertical bars wrapped around the vector letter. Let's apply our mathematical evidence here. Step 1. Identify your components. Let's say we have -1i and positive 3j. Step 2. Apply Pythagoras. You take the square root of -1 squared plus 3 squared. Step 3. That gives you the square root of 1 plus 9, which is the square root of 10. You explain your working clearly and link to the final answer, 3.16 to 3 significant figures. Notice how that negative sign completely disappeared when we squared it. That's because magnitude is a physical length, so it is absolutely always positive.
Section 3, Core Vector Operations. Let's learn how to manipulate the data. When you multiply a vector by a normal number, which we call a scalar, you're just stretching or shrinking that vector arrow without rotating it at all. Imagine our vector A as a piece of string pointing directly to the safe house. If we need to go 3 times as far in that exact same direction, we just multiply by the scalar 3 to get 3a. It really is that simple. If our original vector was 2i plus 3j, multiplying by 3 gives us an expanded vector of 6i plus 9j. The command word you're looking for here is often express. If an examiner asks you to express a parallel vector, you immediately know you just need to multiply it by a scalar. Now, what if the scalar is a negative number? The arrow just flips 180 degrees. It points in the exact opposite direction, but crucially, it remains on the exact same parallel track.
Finding the resultant vector of addition or subtraction is as simple as collecting like terms. You just combine your I values and your j values completely independently of each other. For example, if we have a vector 2i plus 3j, and we want to add vector I minus 2j. Let's think about Sam again. Under time pressure, Sam often panics and tries to add the i's and j's together into one messy, unified number. That is a critical mark-losing error. You absolutely must keep them separate. 2i plus I is 3i, 3j plus negative 2j is 1j, or just j. So your final resultant vector is simply 3i plus j. Visually, if you want to picture this, it's called the head-to-tail method. You draw the first vector arrow, and right from the tip of its head, you draw the second vector. The resultant vector is simply the direct shortcut from your starting origin straight to your final destination. Now, this fundamental subtraction rule is your ultimate master key for position vectors. Finding the path between 2 points always equals the destination's position minus the origin's position. Let's break that down. A position vector, which is usually written as capital OA or just a bold lowercase a, always starts from the absolute origin point 0. If I want to find the journey from point A to point B, which we call the vector AB, I take the position vector of my destination, B, and I subtract the position vector of my start, A. Destination minus start, B minus A. I want you to write that in massive letters on your revision notes right now. When Alex finally stopped just listing facts and applied the specific B minus A rule to his working, his red pen marks instantly transformed into green check marks. It's a total game changer. Section 4. Zero and unit vectors. We are moving into the special edge cases now. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We have helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @theacetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. All right, back to the heist. I want you to think about how we standardize measurements in mathematics when we just want to isolate pure direction. Imagine a vector that is massive, say pointing 50 units east and 120 units north. That's great for plotting a long, complex journey. But what if we just want a compass needle? What if we just want the pure, distilled essence of that direction, without all the bulky magnitude getting in the way? What happens when a vector's length is exactly 1?
This brings us to unit vectors. They are incredibly powerful tools because they give us a pure directional building block of exactly 1 unit. Think of the vector I. It is literally just 1 step to the right. Its magnitude is exactly 1. The vector j is 1 step straight up. Its magnitude is 1. Any vector in the entire universe can be boiled down to a unit vector. It's like finding the fundamental DNA of the vector's direction. In the exam vault, the command phrase "find the unit vector in the direction of" is a very high-value target. Examiners love it because it tests multiple skills simultaneously. So how do we do it? To shrink any vector down to a unit vector of 1, you simply divide the entire vector by its own total magnitude. Let's do a quick find the flaw challenge right now with our student Alex. Alex gets a vector on his paper, 3i plus 4j. He wants to find the unit vector. He confidently writes, unit vector equals 3i plus 4j, all divided by 2. Okay, look closely at that. Where did he lose the mark? He completely guessed the magnitude. Let's correct it with our proper strategy. Step 1. Calculate the true magnitude using Pythagoras, the square root of 3 squared plus 4 squared. That is the square root of 9 plus 16, which is 25. And the square root of 25 is exactly 5. So the true magnitude is 5.
Step 2. Divide the original vector by that magnitude of 5. So the perfect full-mark unit vector is 1/5 multiplied by the vector 3i plus 4j, which gives us 0.6i plus 0.8j. Boom! Full mark secured for the heist.
Conversely, if you add a vector to its exact opposite, you get the zero vector, meaning you've basically traveled in a complete loop and ended up right back where you started. Think about it. If you walk 5 steps north, which is positive 5j, and then you immediately add the negative vector, which is 5 steps south, or negative 5j, your overall displacement is a big fat 0. You have a magnitude of 0 and, uniquely in the math world, you have no defined direction at all. It's a conceptual placeholder, usually written as a bold 0, or 0i plus 0j. It is absolutely vital to recognize this when you're solving complex geometric vector proofs, because showing that a closed shape returns to its origin point is how you prove the geometry.
Section 5, Velocity Applications. This is it. We're stepping into real-world scenarios.
Let's apply literally everything we've learned today to a classic Cambridge word problem. Consider this the final boss level of our heist. We have 2 boats. First, the Antares. The problem gives us a scalar speed of 3 kilometers per hour and a compass bearing of 0-30 degrees. Second, we have the Bellatrix, which is already translated into our familiar I and j component vector language as 2i minus 1.5j. Do you notice the deliberate discrepancy here? The examiner is actively testing your ability to speak 2 completely different mathematical languages and translate fluidly between them. We cannot compare their journeys, and we definitely can't find the distance between them until we standardize this data by converting the Antares into vector components.
To find the components of the Antares, we use basic trigonometry on our compass bearing, turning a diagonal speed into pure horizontal and vertical movements. This is a speed writing challenge, so stick with me. You have to draw a right-angled triangle immediately, either in your mind or scribbled on the paper. The hypotenuse is the speed, 3 kilometers per hour. The angle from the north line is 30 degrees. To find the east component, which is your I direction, sitting opposite that 30-degree angle, we use the sine function. 3 multiplied by sine 30 gives us exactly 1.5. To find the north component, your j direction, which is adjacent to the angle, we use cosine. 3 multiplied by cosine 30 is 2.6. We link it all together. The Antares velocity vector is 1.5i plus 2.6j. Amazing. You've just cracked the hardest lock in the paper.
Now we execute the exact reverse process for the Bellatrix. We take the components, use Pythagoras to find the speed, and use tangent to find the compass bearing. The command word here is calculate speed and direction. Let's provide the evidence. We use Pythagoras on 2 squared and negative 1.5 squared. That gives us the square root of 6.25, which is exactly 2.5 kilometers per hour. That's your speed. Now for the direction. We roughly draw the vector, 2 units east, 1.5 units south. We use the inverse tangent of opposite over adjacent. So 1.5 divided by 2 to get an angle of roughly 37 degrees. But wait, red alert. The framework requires a true compass bearing, perfectly measured clockwise from north. So 90 degrees east plus that extra 37-degree dip downwards gives us a final flawless bearing of 127 degrees.
Finally, by multiplying both of our component velocities by 2 hours and finding the magnitude of the difference between them, we calculate that the boats end up exactly 8.3 kilometers apart. Let's break down that final glorious move. The Antares after 2 hours is 2 times the vector 1.5i plus 2.6j, which equals 3i plus 5.2j. The Bellatrix after 2 hours is 2 times 2i minus 1.5j, which equals 4i minus 3j. To find the exact distance between them, we subtract their position vectors using that b minus a rule. So 3i plus 5.2j minus the entire quantity of 4i minus 3j. That gives us a displacement vector of negative 1i plus 8.2j. Finally, we apply Pythagoras one last time to that displacement. The square root of negative 1 squared plus 8.2 squared gives us 8.3 kilometers. That is a full 6-mark answer executed with absolute perfection.
Take a mental snapshot of this right now. These 5 bullet points are the ultimate master keys to unlocking every single vector question on your exam. You decode the command words, you apply the Peel framework to structure your math, and you manage your time like a pro. If you see magnitude, you immediately fire up Pythagoras. If you see position vector AB, your hand should automatically write b minus a. If you see unit vector, you divide the vector by its magnitude. This is your complete blueprint. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
I really hope this structured journey has clarified 2-dimensional vectors for you once and for all.
But the real question is, how will you apply this toolkit in your own revision moving forward? You now have the absolute blueprint to pull off the perfect mathematics heist, turning those painful red marks into glorious green checks, just like we did with Alex and Sam today. Pythagoras once said, "Thought is an idea in transit." Now that you have the precise tools to perfectly measure your direction and magnitude, where will your academic velocity take you next? Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.